Hi, my name is Sara Moshage. Thank you for stopping by my poster at ORS 2022. In this video, I'll give you a quick run through of the work. So horses have a bone in their lower limb called the proximal phalanx or the P1. And this bone accounts for approximately 25% of the fractures in racing thoroughbreds and standardbreds. This is an issue because when fractures are too difficult to fix or would require a lot of downtime for the horse, often the horse is put down because horses weigh so much that they can't not use one of their limbs. The three remaining limbs will develop secondary issues. So fractures are an important welfare risk for horses. We know from studies in humans, other animals, and horses that exercise while the animal is young during the period of growth to maturity is beneficial for bone health. But we don't know the frequency of exercise or the exact timeline, like when in their life is exercise needed for optimal bone development. One way we can test out different exercise interventions is to do it computationally using finite element models. But in order to build a good finite element model, we need accurate material properties, specifically Young's modulus. So there is a density modulus relationship that exists for horses that's been used to build finite element models. However, it was developed using adult bone. And we really want to focus on what happens if we implement exercise when the horses are young. So this relationship might not work for us. In addition, we know that things other than density, such as microstructure, play an important role in determining bone tissue's mechanical response. The objective of this work was to develop a density modulus relationship for juvenile horse bone and compare it to adult bone, and to quantify the degree to which bone volume fraction can predict Young's modulus. To answer these questions, we use the following methods. So first, the intact bone was scanned in both a clinical CT and micro CT scanner. This is important because we want to develop a density modulus relationship that can be applied to live horses to model their bones and how they're responding to exercise. And in order to do that, we need to build our density modulus relationship off of a CT density obtained from clinical CT, since we can't stick a live horse's limb into a micro CT and get information. In these methods, a lot of the steps are focused on how do we find the precise location of a bone sample within a clinical CT stack and then sample the density there. After the bones were scanned, they were cut into slabs along the longitudinal axis of the bone, and then bone cores were removed with a diamond-sintered coring bit. These were 5 millimeter in diameter. These cores were then embedded in Delrin end caps and compressed till failure. And from the stress strain plot of each core, the Young's modulus was calculated from the linear portion of this stress strain curve. Then these bone pieces that were missing cores, I scanned them again in the micro CT and then used a computer program called Amira to overlay these scans with the intact bone scan. And this allowed me to precisely locate the core with reference to the intact bone scan. And so here you can see the transition from where the cores actually were in this bone slab to where they are in the intact clinical CT scan. After that, I calculated CT density using a linear relationship between Hounsfield unit, which is the intensity of the pixel, and hydroxyapatite phantoms, which are commonly used to quantify the CT density of bones. And then CT density was converted to ash density using this relationship here. We did this so that we could compare our density modulus relationship to the existing one in the literature. In order to answer objective 2 regarding how does bone volume fraction affect modulus, we use some of the same steps. So we locate the actual core in the micro CT of the slab, and then precisely locate the core within the intact micro CT scan and create an image stack for each core. And then in order to calculate bone volume fraction, I binarized these image stacks and then used Fiji to calculate bone volume over total volume. If we focus first on objective one, which was developing a density modulus relationship for juvenile bone, this plot here on the left is showing Young's modulus on the y-axis and ash density on the x-axis. These orange dots are our data points, and this blue line is the best fit line to those data points. And this gray line here is the density modulus relationship for adult bone from the literature. And what we see from the data here is that the Young's modulus of juvenile bone is overpredicted when we're using a density modulus relationship that was developed for adult bone. So juvenile bone and adult bone require different density modulus relationships in order to describe the response of the bone. So you can see the relationship here. It has an R squared value of 0.64, meaning 64% of the variation in modulus is explained by ash density. If we put some numbers to the difference in the adult and juvenile relationships, the root mean squared error for the juvenile density modulus relationship is 97 megapascals, and the RMSE for the adult density modulus relationship is 394. So that's almost 4 times greater. One thing that may be affecting this offset or the disparity between these two relationships is that 80% of the samples for this adult density modulus relationship were cortical bone. They did test trabecular samples, but they found no significant difference in the density modulus relationships when those bone types were separate or grouped, whereas in our samples, all of our samples are trabecular bone. So that could be affecting some of this. If we go over here to this panel, finding 1.2, what happens if we actually put this density modulus relationship to work? These are 2 finite element models. These are developed from a data set of a 9-week-old horse. So this is a juvenile horse. And on the left, this is the modulus distribution if we use the adult density modulus relationship. And on the right, this is the modulus distribution if we use the juvenile density modulus relationship, which is the one we developed. Even just looking at the color distribution, you can see that there's a pretty big difference in which colors are represented in the juvenile model versus the adult model. So if we use the adult density modulus relationship, cortical bone ends up being 2 to 2.5 times higher modulus than it does when using the juvenile density modulus relationship. So this is a pretty big difference. There's some numbers here, you can compare them, but this big of a difference in modulus prediction would really affect the validity of the finite models that we are building using this relationship. If we move over here to the right panel, this is regarding bone volume fraction. So on the y-axis, again, is Young's modulus, and on the x-axis is bone volume fraction as a percent. And you can see it's a linear relationship, although there is quite a bit of scatter. So bone volume fraction is explaining only 15% of the variation in Young's modulus of juvenile trabecular bone in this proximal phalanx. This relationship here is linear and significant, even though the R-squared value is 0.15. As far as the range of bone volume fraction values, here we're going from about 55 to 90, and this range is higher than data reported for adult horses, which was 36 plus or minus 12%. This is also a higher range than human trabecular bone. The minimal explanatory power of bone volume fraction with respect to modulus may be due to differences in the type of young bone present, specifically like chemical compositional differences within the bone since it's so young. We do know that young horses have plexiform cortical bone, whereas adult horses have osteonocortical bone. So we anticipate there being some chemical differences in the composition of the bones of young horses, which may be explaining some of these higher bone volume fraction values when compared to adults. So to wrap this all up, we found that the existing density modulus relationship, this gray line here, overestimates the modulus of juvenile bone, and this will affect the validity of mechanical loading predictions from finite element models. Regarding bone volume fraction, we saw that there's a linear relationship between bone volume fraction and modulus, but overall, density is a much stronger predictor, the higher R squared value, than bone volume fraction is. And I'll remind you that this is ash density calculated from CT density from a clinical CT scan, whereas this data here in bone volume fraction, this comes from micro CT data. Some limitations of this work. The sample size currently was 33 samples, and all the samples were in the longitudinal direction, so down the long axis of the bone. We know that bone is anisotropic with regard to Young's modulus. So in the future, we'll be testing more samples, including cortical bone, but we'll also be testing in the transverse direction to develop more robust density modulus relationships. We will also be further investigating the differences in microstructure of juvenile bone, so other measures of microstructure aside from bone volume fraction, and also looking into chemical differences between the bones. I would like to acknowledge support from the Beckman Institute Graduate Fellowship Program, which supported me for a year, and also the Grayson Jockey Club Incorporated for funding this work. Thank you for your attention. Please feel free to find me at the conference if you have more questions, or you can always email me.